morning. After analyzing yesterday the problem of flexural buckling, which, as I said, is a very important problem for the bottom of the structure. So we need always to keep in mind that if we have a compressed member, almost everything we will have to do also the flexural buckling check. It's not enough to do the compression strength in the plate, we also do the buckling. So after repeating a little bit the basic concepts that you already learned in mechanics of structures, now we move to another check at ultimately this step, which is the shear. So for shear, we could say that we apply basically the theory that we learned in mechanics of structures, scienza di costruzione. Basically, it's a local check. We're going to find out where is the maximum shear stress. Usually with timber, we have to do almost very often, I would say, with a rectangular cross-section. So we don't have funny cross-section like double T or T or something like this. Anything. So we always have, almost always we have this rectangular cross-section. So we go to calculate the maximum shear stress, which is usually on the barycentric, well, it's always the barycentric fiber, using the Jurafsky theory, and we compare this with the design tensile strength. Sorry, the design shear strength. If you remember, we have three different types of shear. We have a shear perpendicular to the grain, we have a shear parallel to the grain, and we have a rolling shear. For a beam, usually what we are interested in is the longitudinal shear. So the shearing along on an horizontal plane along the axis of the beam. The only thing we need to pay a bit of attention is related to the fact that often, as we said when we were talking about wood and moisture, often our timber member is not completely integral. So during the drying process, some cracks may form, and those cracks may reduce the shear strength. So it's quite often to find on a beam a crack like this. And obviously, if this crack is close to the neutral axis, then we have in a region where basically potential, this is a parabolic distribution, we have a region where the tau is very high. So in this region, of course, when it comes to calculating the shear, I mean, this parabolic distribution is the distribution that we would have if the breadth B was constant. However, this is not the case. You are in the wrong class. Yeah. Yeah, that's timber engineering. I mean, now you are probably, I don't know where are your colleagues. Not here. No, not here. After we see, sorry, okay, English because this is an English course. Okay, so we'll see you later upstairs. Okay, go on. So what I was saying is that if the breadth B was constant, then we would have this parabolic distribution using the Jurafsky theory. But of course, if here you see you have a discontinuity, so B is changing, what is going to happen on this parabolic diagram? What do you think? Well, we just remember the Jurafsky formula. No? I mean, you have something like tau equal to S times V divided by J times B. So if here you see you have a variable B, then what's going to happen? B is going to reduce and tau is going to increase. So basically here what is going to happen is something like this. Okay, so we have basically a behavior like this. We have a concentration of tau, of let's say, tangential stresses, due to the fact that we have a reduced strength. Okay? So we need to account for this possible presence of cracks. Because very often, particularly in solid wood, you will find this. So how can we take into account about this, the presence of these cracks? We have two ways. One way would be to increase the shear demand. So basically, to increase tau d. Or the other way would be to reduce the strength. The regulation, you see, use the first way, which is the most logical one if you want, because the shear strength is always the same. What is actually increasing here is the shear demand. So if you look at the regulation say, okay, for the verification of shear resistance of members in bending, the influence of cracks should be taken into account using the effective width of the member. The effective width of the member is this reduction coefficient, KCR, times the width of the section. So, this reduction coefficient is basically equal to 2/3. So 0.67 for solid timber, 0.67 for glue laminated timber, and 1 for other wood-based products. Okay? So we need to remember that when we check a rectangular cross-section of a timber being made of solid timber or glue lam, in our verification, we are going to calculate something like tau max equal to V, well this would be 1.5 V divided by A, where A is the resisting cross-section. Here we need to put D times B, it's called effective, where B effective is B times, let's say, KCR times B. Okay? So we just introduced this coefficient of 2/3, so 0.67. So this is basically a summary of what we already said. And then we need to remember, when it comes to the shear strength, the shear strength is given by the usual formula without the size effect coefficient, because the size effect of coefficient applies only for tension parallel to the grain and for bending parallel to the grain. Now, the important thing to be aware of is how to choose the FVK, so the characteristic shear strength. As we said before, we have three possible planes of shear. One plane which is not, well actually yes, this is one plane. Actually those are two planes, as you can see here. So in this case, you can have a shear plane along this plane here, so basically a horizontal plane parallel to the axis of the beam, or you can have a vertical shear plane. While instead in this case, you see you have a shear plane always parallel, horizontal, but in this case perpendicular to the beam axis. If you remember, we said that corresponding to those three shear planes, there are different strengths, different shear strength. You remember where we have the maximum shear strength along which plane of those three? What do you mean? Right? This, or this? Which one? No.
Vertical parallel to the grain.
Vertical parallel. So what does it mean? This?
Yes.
and this. Let's say this one. Yeah. So this one is the maximum shear strength. Why?
Because it has to destroy the fibers.
It has to shear off all the fibers, which are the strong components of our material. Okay? So in this direction, this plane, we have the maximum shear strength. Where instead we have the minimum shear strength? Which of those planes? Well, thinking at the microstructural wood, the doubt would be between two directions, two planes. If you think about the microstructural wood, what is easier to shear? We said before, not the fibers. If you are going to shear off a plane, any plane that shearing off the less resistive matrix would be a critical plane. So, which other plane? What do you think? Which other plane should be critical here? Yes, which one would be radial tangential? Because here, radial tangential are direction, but we're talking about plane now. Okay, but so any plane perpendicular. No. Any plane perpendicular to the brain. Well, perpendicular to the brain is only one plane. If you think about the brain, there's only one plane perpendicular to the brain. Okay, we just said that perpendicular to the brain is the maximum shear strength. So, if it's not perpendicular, it would be parallel. So any plane parallel to the brain is potentially a weak plane because it's going to shear off only the less resistive matrix. So which planes are here the ones that are parallel to the brain? So potentially critical. This one is parallel to the brain? No. This one is parallel to the brain? Yes. This one is parallel to the brain? Yes or no? This one? No. Some say yes, some say no. Parallel or not? Think about, this is the microstructure. How would you see if this is a beam? What is the orientation of the fibers here? Unless some degrees due to the brain deviation, but we can expect the fiber to be oriented, you see, parallel to this direction here. So, is this plane parallel to the brain? Yes. So it's going to shear off the less resistive matrix? Yes. Okay. What about this? Parallel to the brain? This one. This plane here. This face. Yes. No. Why yes and why no? The fiber we said they are oriented this way. So, is this plane crossing any fiber? If the fiber are oriented this way, they are all oriented this vertical plane. Does it cross any fiber? It's going to break any fiber, this plane? It's going to intersect any fibers? No, unless some small degrees of brain deviation. Okay, so you were saying? No, why not?
Perché se le micre sono in quella direzione piano taglia.
Okay, let's do a microstructure of now. When we deal with an anisotropic material, it's very important to have always in mind that direction of the fiber, otherwise we may get some mistakes. So, the fiber, this is the cross section. So the fiber of wood, they are all in this way. And they are all oriented this way. Okay, so if this is my cross section, the doubt is vertical plane here, parallel to the fiber. Does it intersect any fiber? Of course, I'm now talking about a purely plane, but in the reality, the plane could be something like this, you know, slightly this way. But is there a way to break the wood by not intersecting the fiber in this plane? Yes, there is a way. So this is a potential shear plane where the strength is expected to be very low. Instead, if you consider this case here, now this is an elevation and the fiber are in this way. Do you have any way to break here? So to shear off the beam without breaking the fiber? In this plane, this is an elevation. So now I'm looking in this direction here. Do I have any way to break the fiber? No. So you see, this plane here is where we have the maximum shear strength. And any other horizontal plane, so this one, and the other three, there we are expected to have the lower shear strength. Okay? Now we need to remember. Yes? Yes.
If we cut the section
In this way.
Among the fiber, in the middle of the fiber. I don't know if it can be done, but
This one?
the first.
This one?
Up.
This one?
Yes.
Yes.
We cut the section among in the middle of the
This way?
among the fibers.
Yes, this one. Or you mean something like this?
No. In the middle of the center.
This way?
Yes.
Yes?
It can be done in this way or not?
Potentially, yes. But since to break this fiber, it takes much more energy. If you have a distribution of tau, the same tau will act here, it will act here.
In the same way?
Well, the tau will be the same. The strength, let's call it the strength and mass. The tau is the same, but the strength is completely different. So the strength is much higher on the fiber than between the fiber. It's like having
so there is no difference between cut done in the middle and
no, there is a difference in the sense that if you have this kind of shear plane here, for sure you are going to have a break in this way here. You will never have a break in this way here because this will take a higher load. So as you increase the load, first you get the failure here. And only later you will have the failure here. But this is impossible because your beam will already fail. Okay? It's clear? Now, just to repeat, okay, we understood. Where is the plane of maximum shear resistance and the other plane where we have instead the minimum shear resistance. Based on the microscopic model, all those three planes would have the same strength. In the reality, this is not true. In the reality, if you do some testing, we will find that the strength along those two planes here is lower, which is called rolling shear, is lower compared to the strength along this plane here, which is called longitudinal shear. Okay? This is not explained by the microscopic model. For the microscopic model, 1, 2, and 3 would have the same strength, much lower compared to this. Instead, in the reality, if you do some testing, because the microscopic model, of course, this is an approximation of the reality. The reality is not in this way. So if you do the actual check, then you will find that this one is lower than the other. So rolling shear is lower than longitudinal shear. Now, in a beam, which kind of shear we can expect when we design a beam? So unidimensional element. Longitudinal. So in a beam, you see the beam I'm expecting, if you remember that again the Jurassic theory, you remember that you have a distribution of tau oriented in this way here, along the cross-section and parallel on the horizontal plane. Remember, you studied this in mechanics of structures, and then we repeated also when we were talking about reinforced concrete. So in this case, you have the same tau on this plane, the same shear demand on this section, this plane here, and the other plane there. For the Jurassic theory, if you remember, the two tangential stresses are the same, but we said in our case, of the timber, the shear strength along this plane is much lower compared to the other one, meaning that if you have a failure, the failure will always be parallel to the grain. So we already said if this beam is going to fail, it will never fail in this way by shear. Actually, we would expect, probably if you remember the distribution of tau, we would expect something 45 degrees, like for reinforced concrete. This is absolutely impossible. If you have a failure for shear, the failure will always be in this plane. So parallel, horizontal. Okay? And here you can find, talking about solid timber, usually also blue, not solid timber, usually you find the characteristic shear strength longitudinal, so parallel to the grain, basically, the longitudinal direction. Instead, the rolling shear, if you look here, there is no value for rolling shear, but the regulation said that the characteristic rolling shear can be found in an approximate way by doubling up the characteristic tensile strength of wood perpendicular to the grain. So if you look here, tensile strength of wood perpendicular to the grain, you see is constant 0.4 megapascal, so almost 0, very low. If you double up this value, basically you get 0.8. You see that it's much lower compared to the longitudinal shear. So longitudinal shear is between 3 and 4 megapascal. Rolling shear is 1, less than 1, much lower. So you need to be careful when you design a beam. You need always to avoid details where, for example, the edge of the beam is subjected to some forces perpendicular in this direction. For example, if you have a joint on a three-dimensional structure, we need to be very careful to ensure that you don't have forces coming, for example, for perpendicular member, going to shearing off the beam in the other direction, so producing some rolling shear. Because for rolling shear, as you can see here, the strength is much lower. Instead, you will have to consider rolling shear when you design a two-dimensional member. For example, a panel made of CLT, a cross-laminated panel. In this case, since if you remember, we have different layers of boards which are oriented in a different way. So, for example, if this is longitudinal, this is a longitudinal view. So some boards are oriented this way, but the board in between, they are oriented perpendicular to the grain. Okay? Now, along this plane here, so along a plane parallel to the outer board, what kind of shear are you expecting? If this is let's say, a plane subjected to bending. Longitudinal. So this would be longitudinal shear. So here you have to use FVK. What about the inner layer of boards? What kind of shear are you expecting here? So those are the boards across perpendicular, so something like this. look at this, it's perpendicular to the red. Maybe this one, yes, okay, let's cancel this one. It may be confusing. Rolling shear because you see the boards here. We are like in this equation here. So this one, similar equation as this. The fiber are coming off here. So this is rolling shear. So on a cross-laminated panel, for the intermediate layer, we will have to check the rolling shear. Instead, for the outer panels, for the outer boards, we will have to check for longitudinal shear. Okay? Okay, so remember, this is the kind of failure that we can expect for shear in a given beam. Never track 45 degrees left for concrete. Okay, now bending. We start with uniaxial bending. What we use is basically the Navier formula that we studied in the mechanics of material. So sigma, so this is the strain demand, M due to bending, Y is bending around the Y-axis, and D design is equal to the bending moment due to the external action divided by the section modulus around always the Y-axis. And this shall be less than or equal to the design bending moment resistance. The general formula is this one, where again we have to consider this size effect factor, AH, because we are talking about bending. Just a reminder that this verification is a conventional verification, if you remember. The bending strength is a conventional quantity that has been defined using or considering a simplified bitriangular distribution of stresses and neglecting the possible plasticization of wood in the compression zone, just for the sake of simplicity of the designer. The section module of rectangular cross-section is BD squared divided by 6. And of course, in this case, if you have a failure, the failure is a very brittle failure. Basically, in bending, you want basically to fail the longitudinal fiber. So the fiber are going to be basically failed by tension, the tension zone. The bending strength, characteristic bending strength, again you can find depending on the strain classes. And then you may have what we call biaxial bending. Biaxial bending is quite often a case in timber design because, particularly when we design a roof, in the roof, the purlins, if you have an inclined roof, of course the purlins are arranged in this way. So they are subjected basically to a vertical load. If this is the vertical load can be decomposed into two components. So W times cos alpha and W times sin alpha. This is a typical case of biaxial bending. If you remember, in mechanics of structures, you dealt with biaxial bending by using the superposition principle. So what you did, you basically calculated first, for example, if you have a situation like this, this vertical load, assuming a simply supported beam, this vertical load W cos alpha will induce in your beam, let's do it here, a distribution of stresses in the more stress cross section. So let's use the same notation. So this is y, and this is z. So let's first study the stresses induced by the component of the load in the z direction. The component of the load in the z direction is W cos alpha, and it will induce some bending around the y-axis. So sigma MYE is basically the stress due to bending around the y-axis will be W cos alpha, this is the load, times L squared divided by 8, assuming we have a simply supported beam like this, for the sake of simplicity. Divided by the section modulus around y. What is the equation to find the section modulus in this case? Rectangular cross section, so this is B and this is B. So the section modulus is given by, for the bending around y-axis, B, D, B, B, D squared divided by 6. Okay? Good. Now what do we need to do now? Now we need to calculate the stress distribution due to the bending around the z axis. Okay? So we need to consider, you see here, this load. Wy times sin of alpha. So we will have a sigma mxd So let's go to represent here the stress distribution. How would we expect? Okay, in terms of sign, which sign will we put here and here? So what kind of stress you can expect here? Tension or compression? What about here? Tension or compression? This one compression, so this is minus. So if this is compression, this is tension. Is it right? Yes? No? So this is the load. This is the beam.
Compression on the left and tension.
Compression.
Not here.
No, here we're talking about now. Then we see the other one. First we need to make sure that this is right. Then we go to the other one. So this one would be this way. Bending moment diagram would be where are the tensile fibers, where are the compressed fibers in this beam here? So I can can expect here, this is the beam, this is positive bending moment, so I can expect tension here, compression here. So, is that right? No, it's the other way around. Compression here, and tension here. Okay? Bending moment, positive bending moment. It's clear to everyone? Okay? Now we need to think about this other diagram here. Let's put it this way, and then we need to assign to put the side here. So what do you think here? You have to look at this at the load here. So the load is applying this way. Okay?
Compressione a sinistra e trazione a destra.
Are we sure about this? We need to look at the load. So this is the applied load. So how would you expect this beam to deflect due to this load? You expect to move in this direction or the other direction? If there is the force pointing this direction, of course, the beam cannot go up. So this will move in this way, right? If it's moving this way, it means that it's bending this way here. So again, tension here, compression there. Okay? Now the formula, can you tell me the formula here for calculating this sigma mxd? Now we are basically repeating the Descevenant problem of biaxial magnet. Just what we studied in mechanics of material. We haven't done anything new so far. Okay? So, sigma mxd equal maximum bending moment. Maximum bending moment will be the load times L squared divided by 8. What is the load in this case? Consider W times sin alpha times L squared divided by 8, and underneath, as a section modulus, what do we need to consider? Which length? This one? What is the resisting cross-section for this load applied this way? First of all, which cross-section is the resisting one? First.
The y direction.
No, wait. First of all, what is the resisting cross-section? Then we need to find the section modulus. What is the resisting cross-section? The cross-section that we are going to check. So, the same. It's not different. But we need to be careful because the axis is different this time. So, for bending around Z, so the section modulus is? So, would be, in this case, the width, if this is the axis, the width becomes this, which is D. The depth becomes the width that we had before, so B squared divided by 6. Okay? Okay, so now, get to this point, what you were used to doing in mechanics of structures to check the safety of the structure. So what you are doing then? Yes, once you get to this stress distribution, if I want now to check the safety of this cross-section, using, for example, the permissible stress method that we learned in mechanics of structure, what do I have to do now to complete the safety check?
To check the most stress point. To check the most stress point.
The most stress point. which one is the most stress point? Which ones, if there are more than one? So, the corner, which corner? The top corner, the bottom corner? The bottom corner. So this one is the only most stress point, this? Or there is someone else? The opposite. This one. So here we get the maximum tensile stress, and here we have the maximum compression or compressive strength. What about these points? Are relevant or not? We need to check also these points here. No. Because here you see you have a minus, you would have minus and plus. No, instead in this point you have plus, plus, so we need to sum up the two, minus and minus. So how would you check now the safety of those 2 points according to the permissible stress method? So what would you be doing with this sigma m y d and sigma x m x with this sigma m x d?
We have to see that there is under the sigma admissible.
Yes. So what do I need to do with these two? So I have sigma m y d and sigma m x d. What do I do now with these two values? We sum them up because we said that we have to superimpose here. They are all oriented in the same direction. Now we're talking about sigma, they are all parallel in the cross section. So we need to sum up them. If you want, we sum up with their absolute value, just not to have any problem. And then once I found the total stress, what do I need to do with this total stress?
We have to check if it is less or equal to the resistance strength.
This is what we were used to do, right? Okay, now, if you look here, there is the formulation is slightly different. So we don't sum up the two of them and we compare, of course, in this case, we shouldn't compare with sigma admissible stress. We should compare those two stresses with F and D, right? With the design bending strength. In this case, because we're not talking about the permissible stress method, we're talking about the semi-probabilistic method. So we should check sigma admissible with the design strength. Instead, you see that there is a slightly different design inequality. Where does it come? How can we get from this to this other one? Well, you see, if I multiply by 1 divided by F and D, then I will get something like sigma m y d divided by F and D plus sigma m x d divided by F and D less than or equal to 1. So we get to an equation which is similar to the one that we can find in the regulation. Which other changes we could do here? Why there is, you see here, F M Y D F M Z D. Yes, sorry. If we want to be more consistent, that's right, I made a mistake. Because we are talking about bending around the Z axis, not around the X axis. So this should be M, sigma M Z D. So this should be sigma M Z D. And here, sigma M ZD and ZD. So we are consistent with, actually this is right because the two axes were called Y and Z, not X and Y. Now, the regulation make a distinction between, you see here, FM, YD, and I call this one FM, XD. Why is that? Because the bending strength may be different if you have the bending around the weak axis or bending around the strong axis. Why could be different? Could be different because the size effect, KH, may be different in the two directions. Because the size effect refers to the depth. So if the depth is less than 300 millimeter, then you can use a KH, sorry, it's less than 150 millimeter in the case of solid wood, then KH should be larger than 1. So for example, if you have a cross section here, this one, which is, let's say, 200 millimeter in this direction and 100 millimeter in the other, when you calculate the bending strength FMZD would be the strength for a cross section where you have here, let's say 200 millimeter, and here is 100 millimeter. So FMZD would be KH times K6 times K mod times FMK divided by gamma M. The KH, let's write back. This KH could be larger than 1 because 100 millimeter is less than 150. Okay? While instead, when you calculate FMYD, in this case you have this is 100, this is 200. So FMYD would be KH times K6 times K mod times FMK divided by gamma M. In this case, KH is 1. Okay? So for this reason, to be more general, the regulation consider that along the two directions, you may have different design strength. To take into account that KH may be different along the two bending planes. Okay? So basically, this design inequality now is rewritten to take into account this change. Is rewritten in this way here. Okay? To take into account that the two design values around the two axes may be different. Usually they are very close to each other. In fact, we don't make a great big mistake if you just use the same around the two axes. Okay? And now you see there is an introduction of a new coefficient, Km. Km is introduced here, and then Km is introduced here. Then we do two checks. Why does the regulation introduce this new Km factor? Look here, the factor Km makes allowance for redistribution of stresses and the effect of inhomogeneities of the material cross-section. The value of the factor Km should be taken as follows. For solid timber, rule-up and LBL, for rectangular cross-section 0.7, for other cross-section 1. For For other wood-based structural products, for all cross-section 1. So basically, only if we have rectangular cross-section made of solid timber, foam timber, glulam, or MBL, then we need to add this factor, which is 0.7. Otherwise, we can just refer to this design inequality. And this factor makes, you see, allowance for redistribution of stresses. What does it mean? Let's have a look again to what we had before. Before we said that there is a point where we have the maximum tensile stress and the point where we have the maximum compression strength. If you remember, when we derived the bending strength, we said that this bending strength is basically a conventional variable strength because we wanted just to ignore the potential plastic redistribution that we might have in compression because we said that that would make the calculation more complex. And anyway, it was negligible. Okay? This is true if you have uniaxial bending. If you have, however, biaxial bending, then this compression becomes no longer so negligible. So you would find here that there is a significant region here around this point of maximum compression where the wood is going to plasticize. And this plasticization basically raises the bending strength, the bending resistance. So in order to allow for this increased strength due to plastic redistribution in biaxial bending, the regulation has introduced this Km factor, which is equal to 0.7. So if you want, this is a conventional way to take into account, in a simplified way, the effect of redistribution on the resistance of timber beams, rectangular cross-section only, subjected to biaxial bending. Okay? Is it clear? So we found out how those inequalities were derived and what is the meaning of this Km. So basically you have to apply, you see, Km on both ratios, but not at the same time. So first you multiply by 0.7, the ratio between sigma mzd is fmzd, you do your check, and then you apply the same factor to the other ratio, you do the check. The check shall be satisfied in the sense that this sum of those ratios shall not be exceed 1. As I said before, usually these two, we have only one Fm. So Fmyd is the same as Fmzd, but theoretically it could be slightly different for the reason that I told you before. Okay? So the regulation wants to be rigorous. So for this reason, it's written this way. Okay. Now, second topic of the day, third of the day, because we started actually fourth. We already have here, uniaxial bending, biaxial bending. Now we're talking about lateral torsional buckling. So lateral torsional buckling is a topic that you will study in the course of stability and bifurcation of equilibrium. It's another classical problem of buckling after the Euler problem that you studied in statics. So flexural buckling is the lateral torsional buckling is the problem that may occur in beams subjected to bending, which are made of narrow and deep beams. So usually this problem occurs in beams which are narrow and like the typical problem is a blue laminated timber beam, which is very narrow, we say up to 20 centimeters, and maybe also 2 meters high, perhaps some meters long. You see here in this sketch, you apply the bending moment, and the beam, rather than deflecting only in the vertical plane, The beam tends to basically have a lateral deflection. The beam has a vertical deflection coupled with lateral deflection and torsional rotation. So this is the typical shape, if you want, the formal shape of a beam that is subjected to lateral torsional buckling. Ce l'abbiamo quando abbiamo a che fare con sezioni rettangolari strette e alte. Tipicamente una trave in legno lamellare che è stretta 20 cm, alta fino a 2 metri e lunga può essere anche 20 metri. Okay, so we said this is the problem called as a lateral torsional buckling. We will have to be very careful when we design the timber about this problem here. So the basic theory will be studied, as I said before, in the course of lateral bifurcation, the stability bifurcation structures, where you will write all the differential equations. You will find that unlike the Euler problem, where you had only one equation, one differential equation, here you have two differential equations. Because it's an equation related to torsion, it's an equation related to bending. The two differential equations are in some way connected to each other, so the solution is not so trivial. So, in terms of design, if you look at the Eurocode, we have a design inequality similar to the one that we saw yesterday, talking about flexural buckling. So the idea is that I'm going to calculate, you see, the design bending stress by using the usual formula, M, the Navier formula, M divided by W. And then I compare, rather than comparing this strength demand with basically the strength bending, I compare this with a reduced bending strength, where the design bending strength FMD is multiplied by a reduction coefficient, K crit. This is K crit, you see, it's a factor which takes into account the reduced bending strength due to lateral buckling, like this K CY and CX that we were seeing yesterday. So this reduction coefficient is connected to the phenomenon of lateral torsional buckling. You see, there are some empirical equations. So K crit is equal to 1 for, here we have to define another kind of slenderness, relative slenderness ratio, like the one that we saw yesterday. In this case, we will find there is a different expression to find the slenderness ratio when we talk about lateral torsional buckling. So, relative slenderness ratio less than 0.75, the coefficient is 1, so we don't have problem with lateral torsional buckling. When this relative slenderness ratio is in the range of 0.75, 1.4, we have another equation for K crit. And when instead this is larger than 1.4, we have another equation for K crit. This is basically the curve we are talking about, depending on this slenderness ratio. So, the relative slenderness ratio for bending, you see, is given by the square root of the ratio between the characteristic bending strength and the critical bending strength calculated according to the classical theory of stability. So sigma M crit is the critical value of the stress that we will be calculating in the other course by solving those differential equations, the system of differential equations. And you see, for timber, we will have to use the 5th percentile stiffness value. So again, we will have to use not the mean Young modulus, but the 5th percentile, the characteristic value of the timber Young modulus parallel to the grain. In general, you will find, as a result of this theory that you will develop in the other course, that sigma M crit is a ratio between the critical bending moment leading to your beam to the problem of lateral torsional buckling, and Wy, which is the section modulus. And this is the result. This is pi times square root of 5th percentile of Young modulus time second moment of area about the weak axis this time, so weak axis, Z. Then you have the shear modulus, again the fifth percentile of the shear modulus times torsional moment of inertia of your cross section divided by LF, which is the effective length of the beam, depending on the support condition, the load configuration. Okay? So, this equation here will be demonstrated in the other course of stability. Now, there is a simplified version of this formula. For softwood with solid rectangular cross section, sigma and prick should be taken as, you see, we're talking about now a rectangular cross section, which is, I would say, 99% of our design, made of softwood. 99.9% of our design, let's say. So, rectangular cross section made of softwood. So, sigma and prick is 0.78 times b squared divided by d times effective length times the 5th percentile of the Young modulus parallel to the grain. Now we need to be a bit careful about how to choose the effective length. If you remember yesterday we discussed about the effective buckling length for columns, we said that we need to be careful also there about the plates when we study buckling. In this case, in this table you can find the effective length as a ratio of the span. So, if you have a simply supported beam like this, subjected to uniformly distributed load like this, LF is chosen as 90% of the actual length of the beam. So in this formula, LEF is 0.9 times L. Okay? If the beam is subjected to constant bending moment, then we take the whole length. If the beam is subjected only to a concentrated load in the middle, then it's 0.8 of the length. If we have a cantilever, for a UDL it's 0.5, the actual length of the cantilever, so for a uniformly distributed load. If you have a concentrated force at the free end of the cantilever, then it's 0.8 of the actual length. Okay, now an important thing is to read what is, do you have any question? No. Important thing is to read what is written here. The ratio between the effective length and the span L is valid for a beam with torsionally restrained supports and loaded at the center of the gravity. What does it mean? It means that what is written there is valid when you have, let's cancel here. When you have a beam, if this is the beam, the beam should be restrained, torsionally restrained at the support. What does it mean, torsionally restrained at the support? Beam torsionally restrained at the support. What does it mean? What kind of restraint do I need to have to comply with this? A column may not be enough. It depends how is it connected to this. What is a torsional restraint? Yeah, but torsional restraint, what does it mean? Which kind of degree of freedom should be restrained?
Can rotate.
It can rotate. So this cross section here should be in some way unable to move in this way. Okay? So the classical kind of torsional restraint that we study in a mechanical structure is a kind of fork. So a fork like this, of course this is an approximation. Fork like this, just at the end of the beam, which is preventing this beam from rotating, torsionally rotating. Okay? So these formulas here are true if you have two restraints like this at its ends. you have to have those two torsional restraints. And second, loaded at the center of gravity. What does it mean, loaded at the center of gravity? Well, it means that all the load should be applied on this axis of the beam, which is on the center of gravity. Now, it's true that all the load is applied to the center of gravity of the beam. Which load is for sure applied to the center of gravity of the beam?
Self-weight.
The self-weight. Self-weight is applied to the center of gravity of the beam. However, we usually build a beam to support something else, which is usually above. So all the loads coming from, for example, the roof on the floor above is actually not applied on the center of gravity, but it's applied where? In which axis? Here. Okay, here is applied. Okay? Now this load, which is applied above the center of gravity, your opinion, it's favorable. I mean, what I'm talking about, since most of the load is applied above the center of gravity, is this difference in level, in altitude, let's say, positive or negative in terms of resistance of the beam to lateral torsional buckling? Another way, we said this is the cross section. The beam should be applied, the load should be applied here to get this formula here, this effective level. Instead, we say in reality the load is usually applied here. Is this going to improve or getting worse the situation in terms of lateral torsional buckling? What do you think? Well, we need to think about how this beam is going to deform if lateral torsional buckling occurs. We said that this beam is going to deflect laterally and to rotate torsionally. Now, having a load which is applied here instead of here, does it make things worse or better?
Worst.
Worse. Why? Because it increased the torque moment applied to the beam. So we have an additional torque moment given by the load times the distance E from the center of gravity. Okay? If instead the load was applied on the bottom of the beam, for example, you're going to hang here like a big lamp on the beam. Is this positive or negative? Positive. Why? Because also here we have a torque moment, but this torque moment tends to, while the torque moment before tends to increase the torsional rotation, this other one tends to decrease. Okay, to decrease the torsional rotation. So for this reason, if you read here, if the load is applied at the compression edge of the beam, which is 90% of the cases, LEF should be increased to take into account that we have a worse condition. By how much? Twice the H, so twice the depth of the beam, and may be increased by 0.5 H for load at the tension edge of the beam. Okay? The fact that we are going to increase the beam by twice the depth seems something not important if you are talking about solid timber, like timber beam which is 150, 200, 300 centimeters high. But if you're talking about a nulla beam, which may be up to 2 meters high, you will see that 2 times 2 is 4 meters longer, so it's becoming quite important. So I just wanted to stress that we need to remember about this. We can't just ignore it. It's not negligible for nulla beam. In fact, we will see in an exercise, a work example that we will do, this effect becomes quite important. The other thing I want to point out from the very beginning, when you have longer beams, like let's say Luna beam which is 15 meters long, there is no way that you can get this verification satisfied if you don't provide some lateral restraints along the beam. So this verification here is very critical for our structural method. You will see for a beam which is 22 meters long, if you don't provide any support, so any bracing, there is no way that you can get this verification satisfied. Because you will get to a coefficient K creep, which will be like 0.1. So you are going to decrease by 90% the strength. Because that torsional buckling is a very important phenomenon, very significant. Of course, we need to be careful to always assess the actual restraint condition. Because if, of course, this kind of condition may occur if the beam can move in this way. Now, suppose that your timber beam, you do a floor, and you connect your timber beam to reinforced concrete slab. You do what we call timber concrete composite floor. So you have several joists, several timber beams connect with some connectors to a reinforced concrete floor. Can this kind of beam buckle for lateral torsional buckling? So you have a situation like this. Looking down, you have a number of beams like this. And they are all connected with a reinforced concrete slab above. Okay? This is looking down. Now, in this beam, when I'm designing this beam, do I need to do the lateral torsional buckling check? If I do, what kind of effective length should I consider? Allora, load is applied to compression edge of the beam, but which length do I need to consider?
The length is increased by 2h.
Okay, 2h because the load is applied to the compression edge of the beam. But here, LEF equal. Okay, 2h plus what? 0.9 times L. But now we ask ourselves, can a beam like this buckle for lateral torsional buckling if on top of the beam there is a reinforced concrete slab? No. So, if you cannot buckle, my LEF become 0. Why cannot buckle? Think about it. To buckle in this way, first of all of them should buckle. But then you see this rectangular floor should distort, should become a floor like this. So the concrete slab should in some way fail, which is not possible. Because the concrete slab is stiff in its plane. Okay? For this reason, we need to recognize. You see, the factor K creep may be taken as 1. K creep means LF equal to 0. So K creep 1, so there is no lateral torsional buckling. For a beam where lateral displacement of its compressive edge, so this compressive edge here, lateral displacement of this compressive edge is prevented throughout its length. And where torsional rotation is prevented at its support. So in this case, basically, all the compressive fiber is restrained from moving horizontally because it's connected to a concrete slab. And to move horizontally, the concrete slab should distort. Okay, so it's not possible. Of course, different would be the case. Where rather than having a concrete slab on top, you would have a layer of board, like in a non-floor. Consider a non-floor. In the non-floor, you have some beams, and then on top, you have a layer of bolts. Okay, so beams and then a layer of bolts. Then are the layer of bolts preventing the possible movement of the timber beams underneath? So those are the beams. And on top of the beams, we have some bolts. Okay? So the question is, in this case, what kind of K-crit factor, what kind of effective value should I consider? If you see a number of boards which are connected, let's say, with some nails, few nails, on the beams underneath. So is this layer of board preventing, keeping, offering a lateral support to the compression edge of the beam? Answer? No. What could happen in this case? The case could happen, suppose that one beam tends to buckle here. But you could tell, okay, but this beam cannot buckle because there are the other. But what could happen in this case, you have all the beams buckle together. So this one is going to buckle, and then, since you see here there is no dimensional structure, this displacement is transmitted by each board to the other beam. So you have a phenomenon like this. They are all buckling together. If you have very narrow board, of course, this is the case that you have if you have very narrow board connected with only one nail in the middle. Because in this case, the situation would be like beams connected with some trusses like this. Okay, so as soon as one beam buckled, all the other buckle together. So theoretically, this is the case of a very narrow board with only one nail in between. Of course, if the board becomes a bit wider, and rather than using one nail, you use two, then the effect is a bit better. Because the beam, the board, rather than acting only in tension and compression, can also transmit a certain bending moment. So can also prevent a little bit this rotation here. In my situation, in order to get to this situation here, what should we do here? In order to get to the same situation where no beam can buckle.
Glue together the boards. Glue together the boards.
On the top, we could glue or we could nail another layer of boards to create a kind of grid of boards. So basically, we should widen the board, so instead of using narrow boards, using plywood sheathing, where basically the connection is by using panels like this. If you have a very wide panel, then you see this, to get this displacement, the panel should distort in shear. So you should have a shear distortion of the panel, which is very difficult to have. Okay? So remember that the way to strengthen the flow is actually to have a layer of boards, not only one layer, to have 2 or 3 layers, or to use some bidimensional panel. In this case, then you can say, okay, this panel prevents the displacement of the compression edge of the beam. Or, if you, of course, if you have reinforced concrete, even better. Okay? So be careful to recognize when you design a timber structure, to recognize the actual restraints that you have in your structure. So to see whether the lateral torsional buckling verification has to be done or not. It's not always mandatory. Okay? It's clear what we're talking about here? So again, if we have to use, you see the field percentile mode of elasticity parallel bending value in this formula about it. And then of course depending characteristic and strength. Okay. Now other ultimate mistake, which is a new, if you want, news compared to what we usually do when we design a beam, is compression perpendicular to the grain. So think about one beam. You have one timber beam subjected to a uniformly distributed load or to a series of loads. Where can you expect to have compression perpendicular to the grain in a timber beam? Is there a place, is there a region of the beam where you can expect to have compression perpendicular to the grain? So, the question for you, of course. Yes, grain. In the restraint, in the support region. So, here. Basically, if this is the beam, in this region here. So, basically where the beam is supported. There, you see we have compression perpendicular to the ground. So we need to do a check for compression perpendicular to the ground. Why we never did something like this for reinforced concrete or for steel? Why we never check the compression that you have at the support of a reinforced concrete beam or of a steel? Instead now, we said that we have to do it. But if you think about for example, the M&M problem, what kind of stresses would be those stresses that I highlighted there? Did you consider those stresses in the M&M problem?
We can talk of solidification because they are we are too near to the extreme.
Yes.
So, there is a local effect.
There's a local effect. In fact, if you remember, talking about the M&M theory, we already said, okay, what we said, everything is true, but not in the restraint region. We need to move away from the restraint of at least 1/10 of the beam. So those are local effects. The local effects we have primary stresses, but also secondary stresses. What we call secondary stresses are stresses that are there for basically to make the equilibrium. So for example, these stresses here are not predicted by the M&M theory. The M&M theory only considers the stresses parallel to the beam axis, not the other stresses across them, because those are considered secondary stresses. So, first of all, those stresses here, usually, they are much less compared to the primary stress. That's why we call it secondary stress, because they are, in terms of magnitude, they are much less than the one parallel to the beam axis. So for this reason, since the basic hypothesis of the M&M is to have a material which is homogeneous and isotropic, there was no need to go to make any checks there, because those stresses are less than the primary one, and the material is isotropic, so it has the same strength parallel to the axis and perpendicular to the axis. So those ones automatically, the check here automatically would be satisfied. Because the Descemet problem is true for isotropic material. But timber is not an isotropic material. So for timber, we are going to compare those secondary stresses with a strength which is much less than in the primary direction. So it may happen that in this direction, the secondary direction, the check is not satisfied. Because you have less strength demand, but you have also less strength capacity. So we need to do this check. Okay, so to do this kind of check, the regulation said that we need to calculate the demand of strength, which is denoted as sigma C90D, where C is compression, 90 is perpendicular to the grain, D is design. This shall be less than or equal to the compression strength perpendicular to the grain multiplied by a factor which is called KC90. The strength is calculated as usual by ignoring in this case the size factor coefficient, so we don't have any size factor coefficient because we're talking about compression. And then we have to calculate the demand strength by dividing the design compressive load perpendicular to the grain by the effective contact area in compression perpendicular to the grain. So if this is the beam that we need to solve, we can calculate the secondary stress at the support by dividing the restraint reaction by this effective contact area compression perpendicular to the grade. The effective contact area will be the area that is stressed with this compression stresses perpendicular to the grade, the beam. And this should be calculated, you see, according to this regulation here. So the effective contact area perpendicular to the grade should be determined taking into account an effective contact length parallel to the grade. So the effective contact length parallel to the grade in this direction, where the actual contact length L, so this one here, for example, at each side is increased by 30 millimeters, but not more than A, L, or L1 divided by 2. So basically, the regulation said that if I have a situation like this, for example, I have a beam which is supported on a continuous timber member, the effective contact area will be the actual breadth where the top beam is supported by the lower beam, and this breadth here can be increased by 30 millimeters. But in any case, it should not exceed by 30 millimeters each side, so on the right and the left, but anyway, it should not exceed this distance here, the same distance L or L1 divided by 2. So this means that in this equation, you see, we would have an effective contact length slightly larger than the actual contact length. Why is that? Because we have a stress distribution in this contact length going this way. So if this is a support and we have a beam above here, these stresses here are going to be distributed in some way above. So they're going to diffuse this way. And so this situation, since there is some support provided by the outer part of the beam, this situation is much better compared to a situation like this. So if you have only one cube of wood, you load this cube, it's clear that you don't have any support, so you can have a diffusion of stress in this way. While instead here, you have a diffusion of stress. So in this case, if you do, suppose you do a compression test on a beam like this, you will get much higher resistance compared to doing a compression strength test on only one cube, only one particle. Because you have all the external fiber of this beam are in some way supporting the resistance of the beam itself inside that. So to take into account the fact that we don't have only one cube, but we have the whole beam, the regulation said that we can increase this effective area by adding this 30 millimeter on one side and 30 millimeter on the other side. But of course we cannot do this if the beam finishes here. So if you have a situation like this, then we cannot increase 30 millimeter here. We can only increase 30 millimeter on the right hand side. So consider an effective area only by adding the 30 millimeter on the right hand side. Not on the left, because on the left, of course, the beam is finished. Okay? Of course, in a situation like this, suppose you have a beam which is supported by another beam. You need to do the compression check perpendicular to the grade on both beams, on the beam above and so here, and on the beam below. In this case, the effective area will be taken on the other direction. Okay? right and the left, but on the B that we are checking. The value of the factor KC90 should be taken as 1 usually, unless the condition in the following paragraph apply. So if you have, for example, if you have members of continuous supports, provided that L1 is greater than 2H, the value of KC90 should be taken as 1.25 and 1.5. So if you have that this L1 is sufficiently large, then we can take KC90 equal to 1.25 for solid softwood and 1.5 for blue laminated softwood timber. For members of discrete supports loaded by distributed loads, we have another, now it's a bit boring to say that those regulations are a bit boring, we just need to consider them and to read them. So, for example, in this equation here, so members of discrete supports like here, loaded by distributed loads or by concentrated loads further away, we can take KC90 equal to 1.5, so solid softwood timber, 1.75 for blue laminated softwood timber, provided that L is less than 400 millimeter. In this case, we need to take the compression strength perpendicular to the base, so FC90K from the strength class timber. And then we have another case, which is the ultimate limit state of axial force and bending. So coupled axial force and bending, presoflessione o tensoflessione in Italian. If we have biaxial bending and tension, we basically extend the formulas that we saw before for biaxial bending. You see here, if you cover the first ratio, this is exactly the same inequality that we saw before for biaxial bending. In this case, we need to add another ratio, which is the ratio between the demand in tension and the strength in tension. Again, if you go back to the problem that we saw before, so let's say the Desem theory, in the case of coupled biaxial bending and tension, what you would have done is basically to add to those two stresses that we found before another stresses component due to the tensile force. Okay, so what we've done before, we calculate as sigma MYE, sigma MZE as due to the two components of bending. Then, if we had also tension, we should have to add another sigma given by the tensile force divided by the area to those other two components. And then we would have just checked that the sum is less than the strength, the permissible strength. In this case, we cannot do any more. Why? Because we have different bending strength and different tensile strength. If you remember, for timber, the tensile strength is lower than the bending strength. So the only way we can take into account this difference is to act as a ratio. So as we said before, in this case, we would have a situation like this. Sigma T0D plus sigma M YD plus sigma M ZD less than, let's say, this would be a design strength. Now we divide, we multiply by 1 divided by FD, and then we get sigma T0D divided by FD plus sigma M YD divided by FD plus sigma M ZD divided by FD less than 1. And then we realize that actually these design strengths are different in tension and in bending. And so we need to replace this with Ft0d, and this one will was Fmyd at Fmzd, and then to add this Kn. Remember, that takes into account the plasticization. Okay? So those inequality basically comes by this equation. By remembering that in timber we have different strength in tension and in bending. So we need to sum up the ratios basically. Meaning that if you have a member subjected to tension and bending, you have always to calculate the separate component. So never do this for timber, but you just need to calculate the separate component. So sigma T0T, sigma M YD, and sigma M ZD. Then rather than summing up them together, you just do the ratio with the strength. Okay? If you have biaxial bending and compression, if you don't have problem buckling, then you see in this case you have to consider the ratio sigma C0D divided by FC0D squared. So basically the first ratio is to the power of 2. And now if you look at this relationship basically defines strength domain. The strength domain defined by this relationship is a linear strength domain. So if you were to put here, let's say sigma T, so this would be basically tension, and this would be bending. The strength domain that we get is something like this. So let's do it only the one in tension. Okay? The one in compression, so this is tension, and this would be compression. The one in compression, it's a quadratic domain. So the one in compression becomes a domain like this. Because here, it's a quadratic domain. This quadratic domain is true only if your member is squat. So if you don't have flexural buckling. If you have flexural buckling, then you see if the relative slenderness is less than 0.3, then you have this quadratic domain. Instead, if you have buckling, flexural buckling, because we are talking about form, so if you have flexural buckling, you see again, we have a linear domain, where, however, you see on the denominator now, you need to put the reduced strength. The strength reduced due to buckling. You see there is a K, this reduction factor due to buckling times the strength. So in this case, the domain is something like this. So this is without buckling, and this is with buckling. This would be, let's say, FCD, and this one is KCY times FCD. And of course, the more important buckling, the more narrower domain you get. Okay? Note that for reinforced we were drawing a global M domain, bending moment axial force. For timber, our domain is in terms of stresses. Okay, so sigma n versus sigma t, or sigma, in this case would be sigma c compression. So we need to make sure that our strength demand, so for example, sigma c0d is inside this domain. Okay? This is the domain we've already been discussing now. Last case, I think, is the case of beams loaded in compression. So while before we were talking about this case here was the case of members subjected to tension and bending, or columns subjected to compression and flexural buckling. Now we're talking about the case of a beam, which is mainly loaded in bending, which is also subjected to compression. In this case, we have we may have together the flexural and lateral torsional buckling, because we have a bending, significant bending, and also we can have flexural buckling. How do we account for this? With this interaction formula here. So you see, you need again to separate the stress components due to bending, sigma md, by the stress component due to compression, sigma c0d. Then we do the ratio between those stresses and the reduced strength due to lateral torsional buckling, so K3 times F and D, and the reduced strength due to flexural buckling, K CZ times FC0D. Then the ratio, we do the ratio, we take to the power of 2 the first ratio, and then we get this other domain. So if the inequality is satisfied, then it's fine. Otherwise, we need to enlarge the cross section. The other case, it's a case of compression at an angle of the grain. This is a case that we can have particularly in the joints. So if you have, for example, a carpentry joint, like a king post structure made of wood, in the connection region we might have to check that the compression of a certain angle of the grain, for example, we're talking about something like this. Here, we need to check that the compression at an angle to the grain is satisfied. Okay? Here we have no compression parallel or perpendicular, we have compression inclined at a certain angle to the grain. So in this case, we need to use this relationship here. So sigma C alpha D, so at a certain inclination angle and alpha, FC0D would be the compression strength parallel to the grain, FC90D is the compression strength perpendicular to the grain, and we do this kind of interaction formula using the sin and cosine function. So, in the end, just to close this lecture, about ultimate mistake member design. If we have a beam, what kind of ultimate mistake we need to check? For sure, we need to check strength and lateral buckling, bending. Then we need to check longitudinal shear at the support. And then we need to check bearing over the support, compression perpendicular to the grain. So if you want, this is the new thing that we need to do for timber beam. For columns, flexural buckling always for slender members, compressive strength for squat members, and combined bending and axial force for columns. Last, Corse and diagonal truss systems, tensile strength, If you have a truss system, you have to check the cement for tensile strength, compressive strength including flexural buckling, and bearing and compression at an angle to the grain, like this kind of verification that we saw. Okay, now let's end this lecture here. Now the next step will be to discuss next week about serviceability in state. Now next week on Monday and on Wednesday you do the lecture with Dr. Sciomenta. Instead we do the lecture with me again on Thursday. Okay? So probably on Monday and Wednesday we are going to talk about durability or something like this. Okay? And then we continue with this on Thursday. Thank you and have a nice day.